Sometimes the first derivative of a function evaluated at a particular position is called the marginal cost of that item at that value. And the term marginalizing is essentially using the derivative to predict how much it would cost or what the revenue would be, or whatever the case may be, for producing one more of those items. So in the example I describe in the lecture notes, I describe a situation where, let's imagine Boeing is producing 20 airplanes per month, and they want to know how much it would cost them to produce 21 instead. Like a lot of times with businesses, especially at such expensive items, they wouldn't have huge changes in the amount that they're producing. And obviously, you could use the idea of marginalization to do more than just one, but it's usually it's more accurate when you just marginalize to one item typically. And basically the idea of, let's say the C20 represents the cost of producing 20 and C21 is the cost to produce 21. Well, we'd say if you take the cost of producing 20 and add the derivative at 20 to that, that will give us a pretty good approximation of what it would cost to produce 21. And so the first question is, well, why is that? But if we think about what does C prime of 20 means, again, that would be the first derivative of the cost function at that particular point in time. Or if we see a curve which represents the cost to produce a number of airplanes, it would represent the slope at that exact point on the curve. So we'll just say this is right here, and we would have our slope. But essentially, if we remember that slope is always a quantity that's a rate of change, like rise of a run, etc. And, we could imagine this slope being, whatever the rise of a run may be for the particular situation. But basically, if I only run one, like if I wanted to know how much it costs to produce 21, well, there's only one unit in the run. And so basically the slope would give us the direct rise. Basically, how much would this increase for producing one extra airplane? So naturally, it makes sense to use a value for a slope to predict the next value. And essentially, it would give us a point on the curve right here, which, again, since the tangent line fits the curve perfectly at point 20, shouldn't be too far away from the curve at 21 and is a very good approximation. And yeah, that would give us, it wouldn't be the exact value of the cost of 21, but it would be a good approximation. And all of this we call marginalizing, kind of like using the margin, using that derivative to find the cost of increasing the value by 1. And in the definitions, there's a couple ways that it's written, but I like to think of it more like this, kind of in the example I was providing above, where the cost to produce one more item, where C of x is the cost to produce x, and Cx plus 1 just means one additional item, is equal to approximately the cost to produce x items plus the derivative, the cost to produce the rate at which the cost is increasing at that point in time. And same can be said for revenue and profit. The marginal profit and marginal, again, we would call the derivative the marginal function, whereas this would be the idea of marginalizing in order to approximate how much it costs to produce one more. So let's look at an example. Let's return to the example that we were talking about at the end of class this week. It says return to Jerome's example and find the total cost profit for making 300 furniture sets. And if you remember, I changed this from bar stools to furniture sets because the answer we got was like $900, and that doesn't make sense for bar stools. It says then find the marginal cost for producing those bar stools and use it to estimate the cost of producing 301. So let's kind of imagine that Jerome's furniture is currently producing 300 furniture sets per month or whatever. And they want to know, how much would it cost to produce one additional. So returning to the example, which was a couple pages prior in our packet, the profit function we got was this, and that's what we need to figure out our marginals. So let me just copy that over. And it says cost, revenue, profit, but let's just only worry about profit. P of x was equal to negative 2x squared plus 1735x. And then it was minus something, I don't remember, minus 2250. And this gave us the profit to produce X furniture sets. So if we want to know, well, what's the profit for producing 300? It's kind of like, well, this is what we're currently doing. If you're imagining yourself running the business, you already know how much your profit is for the amount of items that you're selling. So that would be negative 2 times 300 squared plus 1735 times 300 minus 2250. And that would give us a profit of approximately 338,250. And, you know, in the previous example, we found the derivative and we found the maximum profit and so forth by looking at the first derivative. But here, we could use a derivative for a different purpose to marginalize. And, you know, again, same deal. We'd first need to figure out, well, what's the derivative? P prime of x. So let me write that over here. And we already found that to be negative 4x plus 1735 by the power rule. And then we don't need to set it to 0 because that would be for maximization, though that's a useful thing to know. But essentially here what we're saying is, again, you know, kind of using this idea, we can figure out the cost of producing one additional one by figuring out what is the derivative at that point in time, or, you know, what's the slope at the current position. If I'm selling 300 bar stools, I know my current profit, and I can also find the rate of change. Basically, how much profit is each bar stool contributing at what rate? So negative 4 times 300 plus 1735. Again, this is our rate of change of the profit. And basically, for every additional bar stool, it's increasing the profitability by $535. So again, what that's indicating is producing more is good because, you know, derivative positive means it's going up. If the marginal cost function is going down, that means we're losing money for each additional, and we don't want to go that way. Again, kind of applying the ideas of maxes and mins. But we found the maximum to occur at 434, I believe it was. So we'd expect it to be positive, you know, again, looking at the graph up until that point at which we have our max. But anyways, using all of this information, basically, if we add those two things together, we could get the approximate cost of 301. Because again, it's approximate cost of x plus 1 is approximately the cost of x plus the derivative, or in this case, the profitability of producing 301, approximately equal to the profitability of producing 300 plus the derivative at 300. And, you know, adding those two things together, this plus this, 338, 250, will give us our approximated, oops, I missed a digit when I was typing it in. Let me do that again. The approximate profit for producing 301 furniture sets is about $338,785. Again, obviously, we could just use the original function to calculate the exact value, but again, a lot of times we don't have exactly the value of our thing, and we can use the idea instead, where we know exactly how many bar stools we're selling, and we know how much our profit is changing for producing one more. And so let's see what the exact value would be. And I wouldn't expect this to be exactly P301, but if we look at exactly P301, that would be $338,783. It's off by $2, but as you can see, very, very close.